Okay. Yeah, so welcome everyone. Today's the third day of the lectures as part of the Cavalry Summer Program. Today's speaker is Matt Browning. This is his third talk. Matt was a PhD student. He did his PhD at the University of Colorado with Yuri Tumre. After that, he had postdoc positions at UC Berkeley, together with University of Chicago, and then he was at the Canadian Institute for Theoretical Astrophysics in Toronto. In 2013, he was awarded an ERC starting grant for his project about convective heat transport and stellar magnetism. And he is currently an associate professor at the University of Exeter. And today he's going to talk about rotation, convection, and magnetism. And this is part 3. So thank you very much, Matt.
Great, thanks, Aaron, and thanks to you and the other organizers for the invitation to speak. So as Aaron said, this is the third in a series of 3 lectures on rotation, convection, and magnetism as part of this Cavalry summer program in fluid dynamics of stars and the sun and other stars. So in the first lecture, I kind of tried to motivate this topic a little bit by showing you just some observations of rotation and convection and magnetism in stars. And the second lecture had to do with basically some of the basic equations and tools that we use to tackle that subject analytically or numerically, and some of the key results from that subject. So I talked a little bit about geostrophic balance and thermal wind balance and flux freezing and the MHD context, and we did a little bit of applications of that stuff. So the basic punchline of that lecture is that, look, these equations are hard. They are nonlinear equations with many, many degrees of freedom. And so you can't, in general, get all the answers you'd like analytically. They are very difficult systems of equations. And so we need to use kind of different tools to get at the answers we want. And so the story of today is I want to zoom in a little bit on rotating convection and magnetism. I've kind of called the lecture 3 Routes to Rotating Convection and Magnetism. As usual, I'm not going to be able to say all that much in 45 or 50 minutes. So this lecture is more, I want to give you the basic story of today is that I'm trying to argue that these problems are hard enough that we need to use a complete toolbox to attack them. And the toolbox might be what I've called heuristics or cartoons, analytical or semi-analytical theory, and then numerical simulations. And those things that the piece that I want to argue today is that those things tell you about different facets of a problem. They can allow you to answer different questions. And so some of the specific questions I thought we might talk about today as time permits are just, look, when do you get convection in the first place? When do you get a dynamo? Along the way, I'll kind of talk about what a dynamo is and some bounds on growth and any dynamo theorems, things like that. But then we'd also like to assess, so those are things that you might, looking ahead a little bit, you might expect that those are things that are aspects of the state near marginal stability. And so they might be accessible to linear theory, maybe, or semi-analytical theory or something. But we also would like to know some things about the evolved nonlinear state. So once convection gets going and it's rattling around and there's magnetism and rotation and all the rest of it, what actually happens? How strong do the convective flows get? How strong are the magnetic fields you build by dynamo action? And how is all that stuff influenced by rotation? So that's the kind of story. And if you take away one thing from this lecture, I guess my basic argument is that those problems are too hard. The astrophysically relevant ones are too hard to be tackled by one piece of this toolbox alone. Very few of them can be tackled by purely analytical theory. Very few of them can be tackled by just heuristics and cartoon arguments. Very few of them can be tackled by pure numerical simulation because the parameter regimes are just too hard. And so the combination of those things, though, can give us some insight. So that's the story of today. Right, so let's start with the simplest questions and the simplest cartoons. And the simplest question we might ask is, when do you get convection in the first place? So the Astro 101 version of this, the cartoon that we draw in an introductory astronomy class might look something like this. Suppose I have some atmosphere that's stratified as a function of height. In other words, the temperature declines with height in some way that we know a priori. And suppose I've got a parcel of fluid that's sitting at some spot in the atmosphere, and it's got a certain temperature that is just very slightly hotter than its surroundings. So if it's hotter for any most sensible equations of state, it's going to be a little bit less dense. And like the rubber duck in your bathtub, it'll feel a buoyancy force if it's under dense, and so it'll start to rise. So the buoyancy force, so it feels a buoyancy force, it starts to rise. And the question of convection, so that's not an instability, that's just somebody moving things around. If the question is, after it's risen some distance, it looks around and it asks, am I still underdense relative to my surroundings? Am I still hotter than my surroundings? In which case I'll be underdense and I'll continue to feel a buoyancy force and continue to rise. Or am I now that I've gone up a little bit, am I cooler than my surroundings? And in again this Astro 101 kind of picture, we imagine the parcel behaving adiabatically. That is, there's no heat flow in and out of the parcel, or very little heat flow in and out of the parcel as it moves, and it adjusts instantaneously in terms of pressure. So the question then is just, so the parcel behaves adiabatically. Its temperature changes as it moves up at the adiabatic rate. It expands adiabatically and cools. So I've drawn that just to schematically again, a minute on an iPad, as this diagonal line that's the same in both of these plots. So the parcel is doing its adiabatic thing, and the question then of stability is just, as it's risen after it's risen a certain distance, is that steeper or less steep than the background temperature gradient? So in a stably stratified situation, the temperature in the background atmosphere is a dashed line in these two little cartoons. The temperature in the atmosphere falls off less steeply than the adiabatic rate. In that case, the parcel will rise a little bit. It'll have cooled more than the background. It'll now find itself dense relative to surroundings, and it'll sink back down. That's of course the sort of gravity wave situation. And in an unstably stratified situation, the parcel will once it's hotter, it's sort of doomed to remain hotter for all time. So it will continue to feel a buoyancy force. So that's the Astro 101 version, and a version of what's called the Schwarzschild criterion. In other words, the convection will occur if the ambient temperature gradient is steeper than the adiabatic one. You can also phrase that in terms of the entropy gradient. So if the background entropy gradient is negative, there'll be convection. But you guys all know, you've had at least one lecture on fluid dynamics, and probably many, many more than one. So you know that this can't be the end of the story. You know that, for example, in the equations in the Navier-Stokes equations, that there's this viscous term that could impede motion. So that didn't show up anywhere in this argument. There's in reality, there's thermal diffusion, there's pressure perturbation, so all this other stuff we could imagine getting into it. So this isn't too bad to start with. Again, at the Astro 101 level, it tells you that, gee, if the temperature gradient that I would need to carry all the flux in a star by radiation alone is a lot steeper than the adiabatic one, it ain't going to do that. It's going to convect. And sometimes that's all you need to know. But if you seek something, a little bit more sophisticated understanding, you need more than just the cartoon. Similarly, if we wanted to know when you get a magnetic field, when you get magnetic field generation, we could start with the induction equation that we've talked about before. And what I mean when I've asked, when do you expect a dynamo? A dynamo, for our purposes, is just a process to convert kinetic energy to magnetic and sustain it against decay. So the idea is that we put in some arbitrarily small seed field, and the motions in that fluid can amplify that field and sustain it indefinitely against decay. We've already talked about how if the velocity here went to zero, if you just put a magnetic field in a medium of finite conductivity, it'll decay away on some ohmic diffusion time. That's just the diffusion equation with a time scale set by eta magnetic diffusivity, which is one of times some constants is 1 over the conductivity. So in a good conductor, the field sticks around for a long time, and in a lousy conductor, it doesn't. A dynamo basically just taps into the kinetic energy and uses that to build magnetic energy. And qualitatively, again, just at the cartoon level, we'd say, look, the ratio of these two terms, which we use to form the magnetic Reynolds number, probably needs to be big for induction to win, right? That if I want to build, if I want to have positive growth, I might think that the velocity has to be above some threshold relative to the value set by diffusion. Now, if you think about it for that's your maybe first attempt at the problem. If you think about it for a second longer, you might realize it's not quite so simple as that, because look, as I go to higher and higher conduct, so in other words, I can't just make the conductivity very, very small, or very, very high rather, so the diffusivity very, very low, because as I do that, the field gets structured on finer and finer scales. The characteristic length scale of the field goes down and down and down, and so that diffusive term, eta del squared b, which I might approximate as eta times b over that length scale squared, typical characteristic scale of the field, that term is going to get really, really big, even if eta itself is very small. So there's a little bit of mathematical subtlety there that you might again think that okay, having a magnetic Rayleigh number greater than 1 is probably important, but it might not be enough, and so there's a worry at the back of your mind. Still, qualitatively, you might expect that if you wanted to sum up, and this part is true, that if you sum up all of dynamo theory in a sentence, I think it's fair to say that to build magnetic energy, a sufficiently complex flow and a sufficiently conductive medium is likely to work. So you need some flow, which has certain properties that we'll talk about again in a few minutes. But you also need there to be decent conductivity, low diffusivity. Okay, so those are the first cartoons, and now let's go to maybe a slightly more sophisticated cartoon to think about how we quantify those things. As I said, you'd like, for example, in the question of whether or not you get convection in the first place, you'd like to understand how that's affected by viscosity or thermal diffusivity. And so to set that problem up semi-quantitatively, we're not going to really do the quantitative stuff until for a few more minutes, if at all. Let's imagine we've got fluid confined between two parallel plates. So this is the so-called Rayleigh-Benard convection problem. We've got a hot plate at bottom and a cold plate at top. And the question is just, so in the background, there's some mean background state that is motionless. You start with a thing motionless. And so the temperature gradient will just decrease linearly from that hot bottom plate to the cold top plate. That's the temperature solution, the no motion state. That is, and the question is, as I increase that temperature contrast, does it convect or not? And so to analyze that semi-quantitatively, let's imagine you could set it up in this way. We imagine small perturbations around some motionless base state. We'll assume a really simple equation of state. We'll assume the Boussinesq approximation here. And then we might develop the linearized equations of motion and the linearized equations governing the evolution of temperature fluctuations. And by linearized, just to remind you, you've seen lots of examples of this already in Michel's lectures. Basically what we mean is we just neglect quadratic terms in small quantities. That's what we mean by linear. Because we're looking at the amplitude of things right as they're getting going, okay? So the amplitude of the motion is small. So the linearized momentum equation looks something like this. The linearized temperature, the equation for the linearized temperature perturbations looks something like that. So let's think about what that means. So again, we won't solve this analytically just yet. You could imagine that you'd be able to do that. But again, I just want to get a slightly more sophisticated cartoon view. And the slightly more sophisticated cartoon is to say, look, okay, if I look at that momentum equation, suppose that right at onset, maybe right when I'm just starting to get motion, maybe that buoyancy term, the G alpha T prime, might just balance the viscous term. Let's ignore pressure perturbations for the moment. Those probably happen pretty fast. So let's assume that at the marginal state, the velocity is such that G alpha T prime is equal to nu del squared U. And just play around with it a little bit. So if you did that, so G alpha T prime is like nu del squared U. Let's do the standard trick that we've been employing of saying, let's approximate derivatives like 1 over a length scale. Let's suppose there's only one length scale in the problem. That's a very questionable assumption, but let's suppose that there's only one macroscopic length scale, and it's roughly the separation between the two plates. So then equating those two things, U is going to be G alpha T prime times L squared over nu. So then we need a value for T prime, and let's suppose that it's just of order the imposed temperature perturbation. I mean, it's not going to be all of it, but let's suppose that it's in that same ballpark. So G alpha delta t L squared over nu. So then the crossing time for this flow that we're imagining, that's just at the marginal instability, is going to be of order L over U, which you can rearrange to show that that's nu over G alpha delta T times L. Fine. Now the argument then is to say, look, if as this thing starts to rise, if it's got this temperature prediction, that's what's driving, the fact that it's underdense relative to its surroundings, and so it feels a buoyancy force when it starts to rise. If that temperature perturbation weaks away faster than the thing rises, then it's not going to convect, okay? Or there's not going to be much convection anyway. So let's look at, the thermal diffusion time, again, assuming this is one length scale, which is L. The thermal diffusion time is order L squared over kappa. Kappa is the thermal diffusivity here. And so if we want the dynamical time to be less than the diffusion time, we need those two things. We need the crossing time up there to be less than L squared over kappa. So you just equate those two things. And that tells us that this quantity, G alpha delta T times L cubed over nu kappa, has to be greater than 1. And we call that thing, or some version of it, you could write it in lots of different ways, the Rayleigh number. And that's, roughly speaking, it's a measure of the buoyancy driving in the convection relative to viscous and thermal dissipation. And just to summarize, you could write, very often you might write it instead in terms of the temperature gradient in the background state. Here, call that gamma, in which case it's G alpha gamma to the gamma times L to the 4th over nu kappa. And again, the practical consequence is that we need Rayleigh number above some critical value for convection to happen. Now, in the order of magnitude argument, this cartoon, again, that we're developing, that I just did, the critical value was 1. So the critical Rayleigh number, we would say, is 1. In reality, it's usually closer to 1,000. So it's an example of how order of magnitude stuff can lead you astray sometimes, but gets the idea right. And similarly, let's go back to our question of when you get a dynamo and ask it with maybe the next order cartoon. So the slightly more sophisticated cartoon. Let's think about our picture of magnetic field lines as these elastic strings threading through some medium, and they're getting carried around by the flow in the limit. And let's think about the limit of very high conductivity, that is very high magnetic Reynolds number, very good conductor. So the field lines are effectively frozen into the fluid. And in that limit, it turns out that stretching a bundle of these magnetic field lines means amplifying them. Now, that may not be obvious right at first glance, so let me just walk you through it for a second. Again, really blackboard stuff, but suppose we've got a bundle of field lines, and initially it's got some radius, it's got some area A, and it goes some length L. We're thinking about a subset of some longer bundle. We've got the tube, and we're holding it here, and it's got some length L. And I imagine stretching it. Fine. So if the fluid, and again, we're imagining that the field lines are frozen into the fluid. So what the fluid does, the field has to do too. So the mass is constant, so that tells us that the rho v is constant. So rho L naught A naught has to equal rho L prime A prime, where the naughts denote the initial state and primes denote the perturbed state, the stretched state. If it's incompressible, let's just suppose the fluid's incompressible to make our lives easier, then the ratio of those two length scales must equal the ratio of the areas. Fine. Now it turns out, I haven't proven this really, but if you're in this high RM limit, in which the fluid is frozen into the field is frozen into the fluid, then it turns out that the magnetic flux is conserved across as you move these things. And so that implies that B naught times A naught is B prime times A prime. So in other words, the magnetic flux is constant as I've done this stretching. And putting all that stuff together then tells you that the primed magnetic field after I've done this stretching is bigger than the original one by a factor equal to the stretching. So in other words, if I stretch the field, I've amplified it in this frozen, in this limit. So even very simple motions will amplify the field if there's some stretching associated with them. So, as a kind of simplest motion you can imagine in a way, you might think about a random walk. So suppose that we've got a single field line. It's initially aligned with, say, the y-axis. It's got an initial strength, and I've put little points along it everywhere along the axis, each some distance d apart. And at every time unit, I let each point move independently to the right or the left. And they move some distance d. And then over time, and I watch what happens to the field over time. I mean, the point is that the field energy, B squared, will grow with some over that on that random walk timescale. And that's interesting. So effectively, any motion that stretches the field will amplify it. The catch is that when we go look at astrophysical objects, so I mean that's another piece of, we're slowly improving our cartoons. We know that RM has to be big, but really the reason what's happening at some level is that the field lines are being stretched around. So we need motions that stretch the fields. Is that enough? Well, when you look at astrophysical objects, so for example, the galaxy, some debate about this, but the initial fields, galactic scale fields, are plausibly very, very weak, 10 to the minus 17 Gauss or something like that, from a battery effect. Nowadays, they're more like 10 to the minus 6 Gauss. So there's been a factor of 10 to the 11 in stretching. If that were purely by just sort of this kind of random walk thing, you'd expect a very tangled field with lots of reversals and so forth. And that's not really what you see. You see not just not just strong fields, but also ordered fields. There is some global scale order. And we've already talked about in the sun, you see the same, we see this, lots of small scale magnetic chaff, but also a more ordered field that appears as active regions. And that's the global dipole. And it does these nice orderly things. And so we'd like to understand where that order comes from. Another piece, you might think, okay, well, random walk is one thing, that's kind of a crummy velocity field, but you just told me, and you've seen already in Aaron's lectures too, that the sun rotates differentially. It's got a nice smooth, in a way, shear flow associated with it. So I've seen this several times already, but from helioseismology, the surface differential rotation of a fast equator and slow pole, red stuff here is fast, blue stuff is slow, basically imprints to the bulk of the convection zone, and there's this rapid transition to nearly solid body rotation for some distance below that zone, called the tachocline. So there's abundant shear at various spots in the sun. Is that shear flow enough to amplify? Because shearing, is also a shear flow will also stretch and therefore amplify the field. And we'll come back to this in a few minutes, but the basic answer is no, that is not enough to do it either. That would create one component of the field, but you need something to get back the field that you started with. Otherwise, it'll inevitably decay. So the thing that people talk about is these different. One thing people talk about is the idea of different building blocks to dynamo action. So for a small scale field, you might say, as I said before, a sufficiently complex flow and a sufficiently conductive medium might be good enough. But if you want an ordered field, like we see in the sun or in lots of other astrophysical objects, you need a bit more than that. You need something that breaks symmetry, and you need something that kind of keeps the cycle going, if you like. So one effect is the shear, and I'll just demonstrate that people call it, for reasons we'll get to in a minute, the omega effect. So imagine we've got a so-called poloidal field. So we're looking at a sphere. It's got a field line that wraps from North Pole to South Pole. Oriented this way, so you can see. And suppose the equator, so this is the pole up here and the equator down here. And suppose the equator rotates a little bit faster than the pole. Well, the field line is going to be stretched out this way, right? So you might imagine that as a conversion. We know it's an amplification, but it's also converting effectively poloidal field to toroidal field. Thinking about toroidal field wrapping around like a torus, and poloidal field around the poles, more or less. But you need something in order to avoid these so-called anti-dynamo theorems that we'll talk about in a minute. You need something that takes that toroidal field and gives you back poloidal field. Otherwise, the cycle is kind of doomed to end at some point. And one such effect is often called the alpha effect, different alpha effects, but convection in the presence of rotation might be one piece of that. So this was really from papers by Parker, and then developed in the context of mean field theory by Steenbeck and Krauss and Radler and other people. This picture comes from a paper by Peter Olson. The basic idea is, look, suppose I have some toroidal field now, and it's subject to there's a convective eddy that starts to carry that field upwards, but there's rotation, so it twists. Okay, so I go from what was toroidal field up to poloidal. Okay, so there's and then I'm back to colloidal and I have shear and all that stuff. So you might imagine that some combination of those effects, the omega effect or the shear acting together with the alpha effect for convection, could help you to build a dynamo. And maybe if you're really lucky, it ends up being an ordered field. Lots of other effects that we'll talk about too that are very important as well. Meridional circulation, so-called Babcock-Layton effects at the surface, the breakup of active regions, and the diffusion and transport over time. That's thought to be very, very important in the sun, for example. Right, so again, we're building up our cartoon, but there's lots of stuff that we haven't gotten to yet. We haven't talked, for example, about well, anything about the nonlinear state, but also, you kind of have the feeling that we could put some of this on a little bit firmer footing. And the stuff we've talked about so far, you can do some of this analytically, or at least semi-analytically. So if you wanted to set up the Rayleigh-Bernard convection problem analytically, do as we said before, imagine perturbations relative to the background state, construct an equation of motion, a linearized equation of motion, and then look for solutions to that. So you might look for solutions that have some exponential time dependence. And if you write it down in this way, the goal would be to figure out the conditions under which those modes grow over time. So have positive growing S. And usually the name of the game with these things is to try to combine the system of equations down to a single equation that you can solve. So in this example, D here would be a differential operator in the Z direction. You'd have some sixth order differential equation, which is an eigenvalue problem that you can solve. And you can solve it analytically or semi-analytically. The classic reference here, well, I'll just tell you that in a second, but roughly speaking, critical Rayleigh numbers tend to be, in the order of 1,000 or so for non-rotating problems. That's going to depend on boundary conditions. You get a different answer if you've got stress-free or free slip boundary conditions. And really what we mean by the critical Rayleigh number is the critical Rayleigh number for the mode with the wavelength, that has the lowest Rayleigh number. So in general, different modes will grow at different rates. They have different lowest possible Rayleigh numbers for growth that might look something like this. You've seen examples of this already. The mathematics is identical to what Michel's been doing for his lectures on waves. One of the resources the main resource I usually point students to is the kind of Bible here by Chandrasekhar, which is well worth having if you should buy a copy. Mine's kind of been worn off, although I realized as I was starting to do this that even better than buying a copy is to, I don't know if you can see this, I evidently stole this from my PhD advisor 20 years ago and forgot to give it back. So yeah, sorry, Yuri. But supposedly, I'm sure he has another copy. Anyway, these online lecture notes by Suzanne Fielding at Durham are also just kind of walk you through the linear stability calculation in some detail. So I recommend those to you if you're interested. You can also add more and more complicated physics. You could ask how this problem is affected by rotation or by stratification. And if you either can't or don't want to solve the problem analytically, you might do it semi-analytically. I would still class it as an analytical problem, but you can solve it numerically. So this is an example of that kind of, it's an eigenvalue problem that you can solve. This solution is done with Daedalus. I'll talk more about Daedalus in a few minutes, but many of you know it already. This was some work that Simon Lance and Laura Curry and I have been doing in it. We're not interested in critical Rayleigh numbers, really. We're looking at dissipation and rotating convection, but we needed to know the critical Rayleigh numbers for problems that had rotation and stratification and all the rest of it. So you can figure out where you have positive growing modes. If you're really paranoid, as I am, then you can go and then verify these solutions with your initial value problem, your simulation, if you like, and just confirm that just above the critical Rayleigh number for growth, you get growing solutions, and below it you don't. So you can do this at lots of different rotation rates. You can do it as a function of stratification. One classic result from linear theory, which you see pop up a lot, is just that the critical rotation inhibits convection. That, again, at a cartoon level, that makes sense. You've added a constraint on the system. The flow is not free to do what it wanted to do in the absence of rotation. And so you might expect that inhibition, that constraint will make it a little bit less favorable to convect than it does. So the classic result from linear theory is that the critical Rayleigh number for growth scales with the Ekman number to the minus 4/3 power. So as I go up in an Ekman, as I go to more rapid rotation, that is a lower Ekman number, the Rayleigh number goes up. The most unstable mode also changes. So that's some kind of, again, classic feature of rotating convection is that as I go to more rapid rotation, the critical wave number goes up, and so you tend to get smaller and smaller scales of motion in the azimuthal direction. And again, you could quantify the things we've said about when you expect a dynamo as well. So you could put that on a firmer footing. I don't necessarily want to go through this in great detail. Let's see how we're doing on time. Yeah, okay. You can construct an evolution equation for the magnetic energy by just dotting the induction equation with B. Well, it's like this top equation. So the first term is basically the work being done, and the second term arises from the ohmic dissipation, the ohmic resistivity in the plasma. So in the MHD limit, J is just the current density is just the curl of B times constants. So you can rewrite that in the way I've done it in the second line. And then recognize a couple of truths. So you can always write that A dot B cross C is less than the product ABC normed. So we could write this product del cross B dot U cross B that has to be less than or equal to this thing over here. You can also recognize, this is maybe if we're thinking about dynamo action in a sphere of radius A, let's say, it's possible to show that this equality down in the bottom left is true, that the integral of del cross B squared is always greater than or equal to pi squared over A squared times the integral of B squared over that same volume. There's a sort of plausibility argument. You can at least see that sort of makes sense by saying that, look, J cross B, in other words, del cross B, del cross B is of order B over some length scale L, and the lowest current, the lowest del cross B, is going to be associated with the biggest L, and the biggest L present in the system is A, the radius of the thing, right? Assuming it has to vanish at infinity and all the rest of it. So that sort of tells you that you might think that that integral del cross B squared is going to be greater than or equal to B over the largest length scale squared, A squared. So sort of the principle of the thing. So you can, again, use that. So then we have the del cross B dot U cross B is less than or equal to this equality here. The punchline is this equation down at the very bottom of the page, which is that the firm bound on the growth of magnetic energy, that it must be less than or equal to this quantity AU max over pi minus eta, where U max is the greatest value of U within the shell, within the spherical shell, times this integral del cross B squared. And so the best, that suggests that if we want d EDT to be non-zero, if we want a positive growth, we need AU max over eta to be greater than or equal to pi. That's kind of a magnetic Reynolds number, right? So we've got a length scale A, that's the radius of the shell. We've got U max, which in this case is the largest value of U in the thing. And then we've got the diffusivity eta. Now, there's lots of different versions of this and more sophisticated and somewhat tighter upper bounds, but that's an example of the kind of thing you can do. And similarly, when I said that stretching by the flow is not enough, there are a series of what are sometimes called anti-dynamo theorems that tell you what kinds of flows might work as a dynamo. And I guess the hand-wavy summary of that stuff is that you need the motion to be three-dimensional. Purely, for example, there's no planar flow can drive a dynamo. An axisymmetric magnetic field vanishing in infinity can't be maintained by dynamo action. That version is called Cowling's theorem. The one that I think is in some ways most relevant to our discussion is that a purely toroidal field, in other words, something like differential rotation, cannot maintain the dynamo by itself, and so on. So there's lots of different versions of this. You can see Chris Jones's very good lecture notes on dynamo theory in 2008 Lazouche lecture notes. I have some lecture notes from a Roscoff school that some of this stuff is drawn on too, which are less good than Chris's, but they're fine. So anyway, and we'd also like to, again, building up our understanding, now we'd like to start thinking not just about whether you get a dynamo, but what kind of dynamo you get, what kinds of fields do you build. And one way to do that is using so-called mean field theory. So you might expand the field into means, a mean field defined in some suitable way, and fluctuations about that mean. And the motivation for doing that in a way is that, look, often we care particularly about the mean field. We care a lot about whether it's structured on some global scale or is just this small scale chaff, and whether it reverses and all the rest of it. So if you do that, you get an evolution equation something like this: dB dt is del cross mean flow cross mean field plus some term eta, which is often called the turbulent EMF, or the turbulent electromotive force, which is the mean of the fluctuating V prime and B. And then the name of the game is to expand that turbulent EMF. Because of the linearity of the induction equation, you can expand that in a power series in terms of the mean field and derivatives of the mean field. So you might suppose that it's something times mean field B plus some gradients of B and second order gradients of B and third order gradients of B and so on and so forth. And you hope that that series converges, which it may in some cases and may not. So in this the story here is that basically the alpha effect in these kinds of models depends on statistics of the underlying turbulent velocity field. And so you can calculate it in some limits, and you can estimate it or have a cartoon picture of it in other regimes. In some cases, you can actually calculate it exactly. So the example that I sometimes do in Blackboard stuff is for a single helical mode, that is a mode with a well-defined wavelength, and it's got some helicity to it. You can show exactly, this is in Moffat's book. There's a new edition of that out with Emmanuel Dormy, another great reference for you. The alpha effect is given by is related to the kinetic helicity of the flow. And there's a sort of general belief that in many more complicated situations, it's also related to the kinetic helicity of the flow, although it doesn't have to depend just on that, but it could also depend on higher order terms and so forth. Anyway, but there's this general link in many cases between the statistics of the underlying velocity field, and in particular its kinetic helicity, and the generation of mean fields. Right, so now we'd like to ask, we have a sense of when you get a field, when you get convection in the first place, when that convection starts to build fields, and maybe even what kinds of fields you might expect to build. Now we'd like to understand something about the flows and fields that you actually end up building in that non-linearly developed state. So what velocities do you get? What kinds of fields do you build? How do they evolve with time? And so I thought I'd talk about the convection stuff first. And look, in astrophysics, we use, in essentially every stellar model in use today uses a version of what's called mixing link theory. And the goal of mixing link theory is to provide for your stellar structure equations a model for the temperature gradient as a function of the flux or the luminosity of the object. And effectively what it does is it's essentially a crude kinetic theory. So you imagine that the convective blobs behave like particles in a kinetic theory. They travel some well-defined length scale. You have a blob of fluid, and it gives up its heat after some distance, which is usually called the mixing length. I'm not going to go through a detailed derivation of this stuff, but I just wanted to motivate it a little bit. In kinetic theory, I mean, suppose that you wanted to calculate the flux of bugs through your windshield as you drive across the country. And you know the density of bugs per unit volume, let's say, is epsilon, and they're moving in just one direction, let's say, towards your windshield. And so you can figure out that per unit time, right, as you sweep out some volume, you figure out the volume that the bugs sweep through is going to be, velocity times time times the area of your windshield. And the flux to that volume, or that flux through that surface, so number of bugs per unit time per unit area, is then going to be just the overdensity, the number of bugs per unit volume times the velocity. That's all you get, okay? So that's a fairly basic result, but you could imagine that just again, slowly improving our cartoons, this is the origin. You sometimes see people argue that the velocity of the convection in fully developed nonlinear convection might be of order of the flux that it's trying to carry, F sub c in this thing, divided by the density of the fluid. So suppose, for example, that if you just naively suppose that the only energy involved was kinetic energy, rho v squared, it's got a kinetic energy density rho v squared, then that's basically what you get, right? F is rho v squared times v, so rho v cubed. So v is going to be of order f over rho to the 1/3. And dimensionally, actually, if v is set by f and by rho, then that's what your choice is. That formula doesn't involve viscosity or anything else, which could be involved. But if the velocity is only determined by those two things, then that's the formula. Generally, we've got blobs moving in every which way. We've got some blobs moving up. We've got some blobs moving down. And if they cancel out, if they're doing exactly the same, there's no asymmetry in the background. In other words, if the energy, usually we're not caring about the flux of bugs, we care about the flux of energy, which involves temperature and so forth. If all that stuff is uniform, then there's no net flux. But if it's not uniform, then there will be some net flux across this surface. And it's, in kinetic theory, again, you relate it, you might relate it in this way to the mean free path. You suppose that, look, on average, the stuff passing through the surface comes from about one mean free path away. And so you Taylor expands the energy densities at x minus 1 mean free path and x plus 1 mean free path. You assume the velocities are the same in both directions, let's say, to make our lives easy. And you'll end up with an expression for the net flux that looks like this. So if there's some energy gradient in the background state, then you'll end up with a net flux. So that is basically what mixing link theory does. It supposes, the slightly higher level of sophistication is to say, okay, well, I recognize that it's not just kinetic energy. There's also thermal energy. I've got this blob of fluid, hotter than its surroundings, less dense. It goes some distance in the background state. And if it's, so it feels a slight temperature excess relative to its surroundings that's given by, the difference between the background state temperature gradient and the adiabatic one, because we assume the parcel is behaving adiabatically. If it's gone a distance L, the temperature perturbation it has relative to that background is just beta times L, where beta is defined in this way. And the flux, again, is of order epsilon times V, that excess energy, rho Cp, so rho Cp times T prime times the vertical velocity. And then you need some argument for what sets the vertical velocity. So in one limit, you might suppose, is that all the buoyancy work is going into kinetic energy, and that gives you a formula for the you can plug all this stuff together and get a formula for the background temperature gradient associated with this. It looks like this. In actual practice, they take slightly different forms. If you look at the version of mixing link theory that is used today, they all are equivalent to this kind of argument. The classic paper that I'd recommend you look at if you're new to this stuff by Douglas Goff and Nigel Weiss in 1976 that talks about the sort of asymptotic equivalence of various flavors of mixing link theory. Roughly speaking, there are two extremes. In one regime, the convection is efficient, and that gives you a certain relationship between the heat flux and the driving. And in another regime, it's not so efficient, and that gives you a different relationship. And in stellar astrophysics, you use something like this to construct a value for the temperature gradient developed by developed convection. There's an unknown parameter called the mixing length. And look, you might think this is all pretty crummy. I mean, the parcels of fluid don't do this. There's no well-defined parcel, for one thing. There's no one length scale. There's mixing and shearing and all the rest of it. It's better for your sanity, if nothing else, to think of mixing link theory as not a theory of convection, but as a theory of the entropy gradient developed by convection. And for that, it might not be so bad. It might be bad, but it's not obviously bad. And just, again, to go back to what a 1D stellar structure model actually looks like, these are models with MESA of a fully convective M dwarf. The specific entropy in this thing, for any plausible theory of convection, is going to be very, very close to adiabatic. And so part of the details that you might expect a convective theory to be sensitive to are just not observationally easy to probe. Most of the entropy gradient, most of the entropy change in an object like this is set up in this very, very narrow boundary layer near the surface of the star, where there is convection, but there's also radiation, and the convection tends to be much less efficient. In mixing link theory, that entropy changed, and hence things like the radius of the star are really set by the value of alpha, by the mixing length. Similarly, we'd like to ask things about the nonlinear state for magnetism. How strong do the fields get? Another cartoon might be to say that, look, equipartition with the magnetic field, with equipartition of magnetic energies and kinetic energy densities, is probably not a terrible idea. So in other words, the flows probably, the fields probably grow into the point where they roughly are equal to the energy densities of the flows that are sustaining them. You might expect that once you get to that point, you start to shut off the flow, and so you won't get a much stronger field. That is a plausible scaling argument. This is a paper Christensen and 2009 kind of argued for a particular scaling relation that is effectively equivalent to an equipartition style argument. But it's also true that that's not a law of nature. There's many situations where equipartition probably plays a role, but if particularly in very rapidly rotating systems, there are other energies available to you. In particular, we think that in the geodynamo, for example, magnetic energy is much, much larger than the kinetic energy of the convection. It was a paper by Kyle Augustin and collaborators looking at some of these proposed scaling laws. Lots of work on this. I'm going to skip this. Point is just again that cartoons only take you so far. The kinetic energy, the magnetic energy that you observe could be very much more than the kinetic energy in a rotating system, or even in a non-rotating one for that matter. So, and you'd like to know something about the fields that you build, what kinds of fields you build. And again, as I said earlier, mean field theory is a way of exploring some of the things that are out there. It's a nice review by Paul Charbonneau a few years ago that goes into some of this. But there are problems associated with it. It's not, by itself, it's not enough. There are issues, for example, with figuring out when the field saturates, what field strengths you get to in the nonlinear state. Typically what is done is to assume a model, so-called alpha quenching, where the alpha effect, which is encapsulating something about the helical convection typically, that is quenched as the field approaches the equipartition strength. But for example, why doesn't, so a lot depends on your quenching formula. Does it, for example, depend mostly on the mean field, how close that is to the equipartition strength, or on the small scale field, and so forth. So it's a useful tool. All this stuff that we've talked about now is useful, but you really would like, in some cases, to simulate this thing to get a little bit of insight additionally. Ideally, in principle, this is an easy job. We just go simulate the full 3D MHD equations in a rotating spherical thing at actual values of the microscopic resistivities. Unfortunately, we don't have the resources to do that, and won't in my lifetime anyway. So we pick our battles, and because of that, we generally have a sort of hierarchy of approaches. Some models choose to resolve the very largest scales in the system, but that means the flows typically are not all that turbulent. They've parameterized something about the small scale physics. You might also model just small sections of the object, and at higher resolution, more turbulent states, but losing the global spherical geometry, for example. And then finally, there are things that are basically 1D like models, which assume more things about the flow. Mean field theory, I would say, is an example of that, but there are others, for example, the thin flux tube approximation that looks at how magnetic fields behave in a medium like this. That's another example of basically making plausible arguments in order to give yourself some computational leeway. The tools for these things are all they're built by real people. Some of them are in this audience. Keaton Burns, for example, is one of the developers of Daedalus, core developer of Daedalus, really. Several publicly available tools for this kind of thing. We've been using Daedalus a lot lately and like it a lot, but also Rayleigh and Magic for these kinds of problems. So I'd encourage you to go out and just play around with them. They're all freely available. These ones are freely available and easy to work with. Right, so just to give you a sense of what these kinds of flows look like, I'm running out of time here, so I don't have time to talk too much about these things, but this is an example of the kinds of simulations you can do today. This is radial velocity on a particular spherical surface in a model of a deep shell of convection. The upflows are red and the downflows are blue, and you're seeing you can model these things with rotation and stratification and magnetism. Just ask how those things interact. The number of questions you could ask is kind of limitless. I will say one thing that emerges very naturally from these kinds of calculations is just that they act very generically as a good dynamo. You put a seed magnetic field in, it'll grow and be maintained against ohmic decay. And eventually the fields get strong enough to react back on the flows to sustain them. So in this kind of plot, you see the magnetic energy growing, and the kinetic energy in that same flow declines a little bit as the magnetic energy gets up there as you get those Lorentz force feedbacks. And eventually there's a sort of back and forth between these things. The punchline that I would, I guess, like to leave you with in the last few minutes is just that, look, rotation matters. One of the things that emerges very clearly from all these things, from the linear theory, from cartoons, and from simulations, is that rotation matters a lot. It matters for the kinds of flows you drive. These are renderings from, again, spherical shell simulations by Nick Featherstone with Rayleigh. When rotation is very weak, that's the top left corner, convection does what it wants to do. It just gets the heat out. And the convective patterns kind of meander all over. When rotation is strong, down in the bottom right here, this is a sequence of increasing rotation rate effectively at fixed buoyancy driving. The Coriolis forces really constrain the motion. So you can shut off convection entirely if you get to really rapid rotation. You can shut off in just parts of the domain, and you can strongly constrain the motion. So it matters for the convective flows. Those flows transport heat, and they also transport angular momentum. And so unsurprisingly, the rotation matters a lot for that angular momentum transport as well. One generic finding that's emerged from things going back to the 1970s is that if you start one of these things in a state of uniform rotation and let convection develop, that when the rotational influence is fairly rapid, you tend to end up with something that might look solar-like, so fast equator and a slow pole. These are renderings of simulations with different rotation rates. Red stuff is fast, blue stuff is slow. If you go to the other limit of very slow rotation, so high Rossby number convection, you tend to find the opposite, which is more consistent with just parcels conserving angular momentum as they move in or out. So anti-solar differential rotation, slow equator, fast pole. Also affects the magnetic field generation, the strength of the fields you build, but also their character, their spatial morphology. So this is a very well-known example of that from the planetary dynamo community, looking at how the dipole fraction of the field, the fraction of the power that's in the lowest L equals 1 mode, how that changes as the Rossby number in a set of calculations was varied. So as you go to more rapid rotation, you tend to get a more dipolar field in these kinds of things. Now, stratification and going to more supercritical states changes the answer a bit. Lots of outcomes are possible. It also changes the field emergence. I'm not going to talk about this at all, but if you had a given field generated deep in some convection zone, the way it rises through the surface is surely affected by rotation as well. And so we've done some work trying to model that. One punchline I think that emerges from these calculations, which is not obvious by analytical theory, is that you can seemingly build fairly ordered fields that have things like equatorward propagation and all the rest of it just by convection alone, if it's quite rapidly rotating. And as we talked earlier about, it's not clear, where real stars are in that parameter regime sometimes, but rotation certainly affects the kinds of fields that you build. Another example of this, just from some recent papers, the rotation also affects the temporal evolution of those fields too. I'm happy to answer questions about that, but I'm not going to talk about it. And then the final thing I just wanted to mention, because I think it's a nice example of how you can bring all these different approaches together, is just some stuff we've done fairly recently, looking at how rotation affects the convective heat transport. So you find very generically from both simulations and from theory that as you rotate convection more rapidly, it has a harder time convecting, of course, and it has a harder time getting a given heat flux out. And what that means is that you need a larger and larger temperature gradient to carry the same flux out. So we looked at this fairly recently with a set of simulations done by Laura Curry and Adrian Barker with a couple of different codes, Daedalus and NEC 5000, 2 different setups. And one pleasing thing here is that these little symbols are a series of simulations at different rotation rates. And the lines correspond to predictions of a particular theory. And the theory, just to give you a one-slide summary, was basically that, look, you calculate the linear growth rates at each I should say that there are other ways of arriving at the same scale, so I think that is quite robust. But the particular theory that we kind of explored in this paper was the simulations and then calculating the linear growth rates as a function of rotation rate at each k. And then you kind of argue, well, look, I've got this sea of modes that are growing at all these different rates, and you suppose that they interact non-linearly, and the time scale in which they interact, the thing that really sets their amplitude, is that they, if the cascade is local in wave number space, the characteristic time scale is for nonlinear actions is just their local overturning time. And so you equate, basically, in a steady state, you might argue that the linear growth rate is roughly comparable to the turnover time on each scale. And then going back to another cartoon that we drew, we assume these sort of MLT mixing length style links between temperature and velocity perturbations. And you can compare that to lots and lots of different rotating F-plane calculations of convection, which Laura and Adrian did over the course of several years. And I think, talk to me if you're interested, or talk to Adrian over the course of the program. But I think the results of this were pretty good. For me, I really enjoyed this paper because it brought together these different approaches of cartoon models and linear theory and simulation. But even in this very simple problem, convection in a box at different latitudes, Busenesque, by the way, some things worked really well and some things didn't. And one of the, basically whenever you get a shear flow, that really led to some problems with the simple, we did not get very good agreement between the simple rotating mixing link theory and the results of the simulations. So that was interesting. More generally, if you go back to the problem that I mentioned as a motivation in lecture 1, we'd have to understand whether you could lead to convection, you could lead to the inflation of low mass stars. There's a problem involving the heat transport as a function of rotation and magnetism and all the rest of it. And that is still an unsolved problem because it involves not just rotation, but also the interaction with shear, how you interact with magnetism. And I guess my general plea to you, I'm going to stop here in a second, is that, look, I've talked about a bunch of different things. In the course of these 3 lectures, I've tried to argue that every star convex at some level. They all rotate, they're all magnetic. Most of that magnetism involves dynamo action, probably involving convection in lots of cases, coupled to rotation. Rotation matters a lot in both determining what kinds of fields you build and in the properties of the heat flow itself. And the problems, we don't have a predictive theory of all this stuff, how this goes together. I guess the real lesson I want to leave you with is that, look, these problems are hard enough and interesting enough and challenging enough that you probably won't solve them by just one of these different approaches, right? They're too hard for pure analytical theory in many cases. The parameter regimes are too challenging for nonlinear simulations alone. And so it's by this kind of combination of cartoons and analytical modeling and simulations that we can learn some stuff. I'll stop there. Thanks very much for your time. And thanks for being a great audience. Thanks, bye.